Warm welcome to another video where we'll be discussing the problems of the given question paper from the unit 2, where the previous problems is already been covered in my previous videos. So there is a question which states that the maximum power transfer theorem for the AC circuits, find the value of ZL and the value of maximum power that is transferred across it for the circuit which is shown in the figure 3a. So this is the figure. So you have to calculate the maximum power that is transferred across the load ZL. So before moving on to the problem, you should make sure that you know the formula of the maximum power that is transferred across the load RL for AC circuits, which is V square TH divided by 8 multiplied by RL. VTH is the Thevenin's equivalent voltage. Now how do you calculate the value of VTH? VTH is basically the voltage across your J8 ohm resistance, and RL is the load resistance value. So the given figure, which is 6 minus J8, this has J8 ohm impedance and 10 at an angle 0 degree volts. So VTH, which is voltage across J8 branch, which is equal to, by applying your voltage divider rule. So by applying your voltage divider rule, you get as 10 at an angle 0 multiplied by the voltage across the calculating branch divided by 6 minus J8 divided plus J8, which will give you a value equal to 13.333 at an angle 90 degree volts, which is the value of VTH. So we have calculated the value of VTH. So next we have to calculate the value of load resistance RL. So now to calculate the value of load resistance RL, we should know the whole value of that is net impedance of the given circuit, which is obtained by short circuiting your voltage source. So when you short circuit your voltage source, the branch is reduced as follows. So you can see here that is 6 minus J8 ohm impedance is in parallel with the J8 impedance, J8 ohm, which will be, and the net equivalent would be, Z equivalent would be, that is the net equivalent of the given network would be 6 minus J8 multiplied by J8 divided by 6 minus J8 plus J8, as both the impedances are in parallel. So they are in parallel combination, that is 6 minus J8, which is in parallel with the J8. So you get the value which is equal to 10.666 plus J8 ohms, obviously. So which is in the form of Z, which is equal to RL plus JXL. Obviously, by comparing these both the equations, you get the value of RL as 10.666 ohms. By comparing with this both equations, you get the value of RL equal to 10.666 ohm. So by the formula, we know that V square TH divided by 8 multiplied by RL. Substituting in the corresponding values, we get as 13.333 square. 13.33. Obviously we should not consider the value of 90 degree angle because we cannot square it, and another point is that you cannot since the voltage is a scalar quantity, not a vector quantity, so you can neglect the value of the 90 degree. That is not 90 degree is neglected, obviously. Divided by 8 multiplied by RL is 10.666, which will end up with the value equal to 2.083 watts. So the problem statement is basically you have to calculate the value of the maximum power that is transferred across it, and you have to calculate the value of ZL. So the value of ZL is calculated, which is 10.66 plus J8 ohm, and the maximum power that is transferred is 2.083 watts. This is watts across the given load impedance ZL. So moving on to another problem, which is a series RLC circuit has a resistance equal to 2 ohm, inductance that is 10 millihenry. What the value of capacitance would produce a resonance at 10 kHz frequency if the circuit is connected to 230 volts AC supply? Find the value of current and energy stored in the inductor during resonance. So a series RLC circuit, which is a resistance and inductor and capacitance, which is connected in series with a 230 volt source. Obviously this is a 230 volt AC voltage, AC supply, find the value of current. So you have to calculate the current that is flowing through this branch. So this is a question of 3B. So 2 ohm with 10 millihenry, and you have to calculate the value of capacitance. Since they already given that the circuit resonate at a frequency equal to 10 kilohertz, so your resonating frequency is equal to 10 kilohertz. We know the formula equal to 1 by 2 pi root LC. So in order to calculate the value of C, just square the equation, which is F square, which is equal to 1 divided by 4 pi square L into C, F square, which is equal to, by squaring the equation. So just calculate the value of C, which is 4 pi square multiplied by L multiplied by F square. So C value is calculated as 1 when divided by 4 pi multiplied by the value of inductance, which is given as 10 millihenry, and the value of resonating frequency, which is 10 kilohertz. So you get the value equal to 25.3302 nanofarad. So the value of C is calculated. And another question is that if a circuit is connected to 230 volt AC supply, find the value of current. So you have to calculate the value of current which is flowing through the circuit, and the energy stored in the inductor, that is, let me call it as EL, which is energy stored in the inductor. So at during resonance, which is the important point, is that you have to calculate the value of current as well as energy stored in the inductor during the resonance. So during resonance, we know that your net impedance of the circuit due to resistance, due to inductance, and due to capacitance equal to, that is, the net impedance of the whole circuit is equal to resistance R, which is 2 ohm. So by Ohm's law, we know that V is equal to I into R. So I need the value of I, which is 230 divided by Z, which is 2 ohm, which is equal to, so you get 2 ones are 2 and 2 ones are 2, 1 remains, 2 5s are 10, 115 amperes. Yes. And now the energy stored in the inductor, which is given by the formula as half Li square. So you know the value of inductance, you know the value of current. We can calculate the energy stored in the inductor as half multiplied by the value of L as 10 millihenry multiplied by 115 whole square. So yes, 0.5 when multiplied by 10 millihenry, and again the current square, half Li square, which the energy stored in the inductor as 66.125 joules. So this is how the problem is solved. Quickly moving on to the next question, where on question 4a is already discussed in a previous video of electrical networks. That is, all the theorem related problems is discussed on the electrical networks playlist. You can go check it out. And fourth big question, which states that, so there is a coil, states that there is a coil of resistance R as 10 ohms and inductance of 0.5 Henry is in parallel with a 400 microfarad capacitor. So calculate the value of resonant frequency for the impedance to act as non-inductive reactances, as well as find out the value of impedance. So the problem statement is simple, which states that the resistance and inductance are in series. They are connected in series, but they are wholly connected in parallel with the capacitance. So this network obviously represents a tank circuit, where your resistance and inductor is in parallel with the capacitance of 400 microfarad capacitance with a 10 ohm resistance, and 0.5 Henry is your inductance value. So I have to calculate the resonant frequency of the given network. So the tank circuit, since the given network is of tank circuit, is a tank circuit. where R and L are in parallel with capacitance C. So yes, the frequency is given by the formula 1 by 2 pi root 1 or LC minus R divided by L to the power whole square. So on substituting the formula, you get it as 1 by 2 pi root 1 over LC minus 1 divided by 2 into 3.141515. So 1 divided by L, that is L is nothing but 0.5, when multiplied by 400 microfarad capacitor, 10 is to minus 6 minus resistance R is 10 ohm divided by inductance value 0.5 to the power whole square. Obviously the square root applies to the whole both the terms. So yes, on calculating you get the value equal to 10.8 hertz, which is 10.8 hertz. And now another question statement is that you have to calculate the value of impedance as well. Which states that find out the value of impedance as well. So in order to calculate the value of impedance, obviously the direct formula is L divided by RC. So what is the L value is 0.5 divided by 10 multiplied by 400 into 10 raised to minus 6. So we get the whole value equal to 12.5. I hope so. Check it out as 0.5 and divided by 10 multiplied by 400 multiplied by 10 raised to minus 6, which gives a value equal to 125 ohm. And if for the same problem statement, if they ask to calculate the value of admittance, which is obviously the reciprocal of impedance, you can calculate it by just taking the reciprocal of it, which will be RC by L. So this is the answer. So they have asked to calculate the value of impedance, as well as they are also asked to calculate the value of the frequency of the given tank circuit. Moving on to the next question, which is Unit 3, question 5a, which the following question is, for the circuit shown in the figure 5a, the switch has been closed for a long time. Figure 5a, which is here. So it states that the switch has been closed for a very long time. That is, initially the switch was in the closed condition. So the current was flowing through this and through this. So this branch particularly. So it has been open at time t is equal to 0. You have to calculate the value of I at time t is equal to 0 plus, and you have to calculate the value of voltage at 0 plus. That is, 0 plus basically stands for the time after your action is taken place. An instant of time just after the action is taking place. The action may be either it may be of opening the switch or it may be of closing the switch. And next, the respective first derivative, which is di by dt at 0 plus and dv by dt at 0 plus. So 4 parameters should be calculated in this problem. So figure 5a is here. Initially, the problem statement is the switch had been closed for a very long time. .1 farad. So this is a 4 ohm resistance and a 0.25 Henry, 2 ohm. Basically, the switch has been closed initially. That is at a time t is equal to 0 minus. So initially, that is t at 0 minus, that is before the switching action taking place, before the switch had been closed. So as we know, since it had been closed for a very long time, your inductor acts as a short circuit, whereas your capacitance act as open circuit. So I assume that you know the basics of the switching circuit. That is, at just a quick review, that at t is equal to 0 minus, that is for a very long time, the inductance act as your open circuit, I mean the short circuit, whereas your capacitance act as open circuit. So at any instant, at the switching instant, this open circuit, this inductor act as open circuit. This is for a very long time. This is for a very long time. That is, it may be of 10 minutes, it may be 15 minutes, etc. This is for at any instant. At the time, at any instant, where your inductor act as open circuit, whereas your capacitance act as short circuit. So applying these basics of this to this problem, so yet since it has been closed for a very long time, your inductor act for a very long time, your inductor act as short circuit, whereas your capacitance act as open circuit. Since it is an open circuit branch, there will be no current obviously, so the resistance remains the same. No changes with the resistance even at the time of switching or before the switching. So yes, you have to calculate the value of current, which will be I is equal to V divided by R equivalent, which will be 12 divided by, obviously these are in series. If you just open this branch, you can see that 4 ohm and 2 ohm are in series, which will be 6, which will be equal to 2 ampere. So that net current that is flowing through the circuit is 2 ampere at 0 minus, obviously at 0 minus, 2 minus. That is the 0 minus basically stands for before the switching action that is taking place. So yes, you have to calculate the value of at 0 plus. In order to calculate the value of the current at 0 plus, you should make sure that you know the basics fundamentals of, that is, current through the inductor doesn't change simultaneously. That is, current through inductor L does not change simultaneously, which simply means that is when the current that is flowing through inductor before the switching action takes place will be the same current which is flowing through the inductor even after the switching that had been taken place. Similarly, for capacitance, voltage will be same before the switching takes place and even after the switching takes place. Obviously, both these conditions occur at that instance. I hope that is clear to you. And since we know that inductor is short circuit, same current will be flowing even after the switching action takes place. So I of 0 plus will be equal to 2 ampere. So we have calculated the value of I of 0 plus, and similarly they have asked to calculate the value of voltage across your capacitance. Please note that the voltage across capacitance before closing the switch will be same after closing the switch. So hence you should know the value of the voltage across this, because even if you know the value of the voltage drop across this 2 ohm resistance, will be the same voltage drop across your 0.1 farad capacitance. So voltage at 0 minus will be equal to current that is flowing at before instant multiplied by the resistance, which is 2 ohm resistance. It should be 2 multiplied by 2, which is equal to 4 volt. That is, V of 0 minus is 4 volt. Since across the capacitance, since you are calculating the voltage across the capacitance will be same even after closing the switch, as we have discussed here. So yes, the voltage across 0 plus will be also equal to 4 volts. So next, we have to calculate the first derivatives of current and voltage respectively, which will be, so that is, we have to calculate the value of the respective first derivatives, which is di by dt at 0 plus and dv by dt at 0 plus. So before calculating these values, you should know the formulas of voltage across the capacitance and voltage across the inductance. Similarly, current across the inductance and as well as the current across the capacitance. There is current through the capacitance and current through the inductance, not across it. So yes, the voltage across capacitance is given by the formula equal to 1 over C integration of I dt, and current through the capacitance is given by the formula equal to C into dV by dt. Similarly, voltage across the inductance is given by the formula equal to L into di by dt. Similarly, current through the inductor is given by the formula equal to 1 over C, which will be integration of V dt. That is 1 over L integration of V dt is the current through the inductance. So applying KVL to this circuit, which will be mean voltage is equal to voltage drop across inductance as well as voltage drop across capacitance, which will be VL plus VC. So it's very clear, that is, mean voltage is equal to voltage drop across inductance and voltage drop across capacitance, which would be V is equal to VL plus VC. So since you know that voltage, the value of voltage which is equal to 12 volts, which will be equal to VL. The VL is nothing but the voltage across the inductor, which is L into di by dt, plus voltage across the capacitance is given by the formula 1 over C integration of I dt. So yes, since we have to calculate the value of di by dt, yes, in our equation we have the value of di by dt to be calculated. So obviously this all values to be calculated at time t is equal to 0 plus. So 12 is equal to L into di by dt at time 0 plus 1 over C. This integration is from before closing the switch and after closing the switch I dt. Okay. This obviously this integration value will be equal to 0 because as lower limit as well as your upper limit is 0 0. So S 12 is equal to the value of inductance is 0.25 multiplied by di by dt at 0 plus. So 12 divided by 0.25 is equal to di by dt at time 0 plus. So di by dt at time 0 plus, which will be equal to 48 ampere per second. Current SI unit is ampere and time is seconds. So you get the value of di by dt as 48 ampere per second. Next is we have to calculate the value of dv by dt at time 0 plus. That is dv by dt at time 0 plus is to be calculated. We know the value of the current through the capacitance is given by the formula IC is equal to C into dv by dt, which is obviously which is required in our problem statement. So all this will be calculated at time t is equal to 0 plus. So IC at 0 plus is equal to C multiplied by dv by dt at 0 plus. We know the value of capacitance, but we don't know the value of the current that is flowing through the capacitance at 0 plus, that is after the switch has been opened. In this case, as you can see here, the switch has been opened at time t is equal to 0 plus. So to calculate the value of current that is flowing through your capacitance at a time t is equal to 0 plus, that is after opening your switch, which will be for this, let it be as it is, 2 ohm. The switch has been opened at time t is equal to 0 plus, because in our problem statement initially the switch was at the closed position, but now it has been opened. So since it will be open circuit to the capacitance as well. Yes. So plus minus 12 volts, 4 ohm and 0.25 Henry, 0.1 farad. As I've already discussed, at instant of switching, that is at any instant of switching, your inductance act as open circuit. Similarly, obviously switch is obviously an open circuit condition, and your capacitance at any instant of switching, the switch has been opened at that instant at time t is equal to 0 plus, where capacitance is open circuited. I mean short circuited. The capacitance is short circuited. Yes, if we short circuit the capacitance, since you can see that there is open circuit at what, at a time t is equal to 0 plus, there will be no current that is flowing through the entire circuit. Thus the current obviously will be flowing to 0 plus will be also be 0. That is the current which will be flowing through our capacitance will also be equal to 0 amperes. Since it is open circuit, no doubt there will be no current that is flowing through the entire network. So yes, we have found out the value of 0 plus, IC at 0 plus. So 0 is equal to, the capacitance value is C is 0.1 farads. Yes, 0.1 multiplied by dV by dt at 0 plus. So you get dV by dt 0 plus as 0 volts. So yes, we have calculated the value of I current at 0 plus as 2 ampere, and we have calculated the voltage 0 plus as 4 volts. Similarly, di by dt at 0 plus as 48 amperes and dV by dt at 0 plus as 0 volts. So hence we have met all requirements of the problem statement. This is how the problem is solved. the next question, which is a series RL circuit with resistance 10 ohm, inductance 5 Henry. For voltage 100 volts is applied to it. So this is the circuit diagram where your resistance 10 ohm and inductance 5 Henry is connected in series across the voltage source 100 ohm, and you have to calculate the value of current and inductor voltage at 0.5 seconds after its excitation. The meaning of this point, after its excitation, basically stands that that is the whole circuit is connected to a switch where the switch is opened before initially and it is closed at time t is equal to 0. So the main purpose of the whole question is you have to calculate the value of current after closing the switch, that is at 0.5 seconds. So yes, the formula, which is V by R into 1 minus e to the power of minus R by L into T. For the RL circuit with a switch, the formula of current is given by this equation. So I is equal to the value of voltage source is 100 divided by resistance is 10 ohm, and 1 minus e to the power of minus the resistance is 10 and multiplied by time of 0.5 seconds. Since you have to calculate the value of current at 5 seconds, make sure that the value of time is in seconds and the value of inductance is 5 Henry. So upon calculation, you get the whole answer as 6.321 ampere. So this is the current which is flowing in the circuit after the switch is been closed, which is obviously at time t is equal to 0. So this is the current that is flowing through the circuit after the switch had been closed, that is at 0.5 seconds. Is at 0.5 seconds, the current which is flowing in the circuit is 6.321 amps. And you have to calculate the inductor voltage. So inductor voltage VL is equal to L into di by dt. Here we can see that we know the equation of current, which is this. So you have to just differentiate it, d by dt with respect to time. You have to differentiate this equation, which is V by R into 1 minus e to the power of minus R by L into T. So on differentiating, you get obviously V by R is constant, LV by R, and you have to differentiate this with respect to time, which will be 0 minus e to the power of minus R by L into T. On differentiating it, as we get minus R by L. So R it cancels and minus into minus will be plus. So we'll be left out with V into e power minus R by L into. So this is the old equation of voltage across inductance. So VL, which is equal to V, where the voltage value is 100 volt source. So 100 when multiplied by e to the power of minus resistance is 10 divided by inductance value is 5 Henry when it is multiplied with the time of 0.5 seconds, which will be equal to 36.789 volts. So the voltage across inductance at time t is equal to 0.5 seconds is 36.789 volts. Another question is that time at which the voltage across resistance, you have to calculate the value of time. So the third case is you have to calculate the value of time where your value of voltage across resistance becomes equal to your inductor, that is VL. So the voltage across resistance is given by the formula I into R. Similarly, it is L into di by dt. We know the value of current. So the voltage across resistance will be I into R. We know the value of current as V by R multiplied by 1 minus e to the power of minus R by L into T, and resistance of this equation. So you get the value of voltage VR as V into 1 minus e to the power of minus R by L into T. So this is the voltage drop across resistance, and voltage drop across inductance is already calculated, which is V into e to the power of minus R by L into T. So VV get cancels. 1 minus e to the power of minus R by L into T is equal to e to the power of minus R by L into T. Upon transferring this term into across RHS, which will be 1 is equal to 2 into e to the power of minus R by L into T. So 1 by 2, which will be half, which will be equal to 0.5 minus R by L into T. Taking ln on both sides, ln 0.5 is equal to minus R by L into T. So ln 0.5, which is the answer is minus 0.693 is equal to minus R by L into T. Minus minus get cancelled. So 0.693 is equal to R by L into T. Since we have to calculate the value of time, so 0.693 multiplied by inductance value is 5 Henry and resistance is 10 ohm, multiplied by 5 divided by 10, which is equal to time t. So time t will be 0.693 when multiplied by 5 divided by 10, which will be 0.3465 seconds. So at time t is equal to 0.3465 seconds, your voltage across resistance and inductance becomes equal. At this time, your voltage across resistance becomes equal to voltage across your inductance. So we have calculated the value of time. So another problem of 6a, which is for the circuit shown in figure 6a, if the switch is closed at time t is equal to 0, find the second derivative for the inductor current at time t is equal to 0 plus. Yes, at time t is equal to 0 plus, which is this circuit which is given here. So you have to calculate the value of second derivative current, that is you have to calculate the value of d square I by dt square at time t is equal to 0 plus. You have to calculate the second derivative of the current of the inductor current, basically IL. So yes, let us calculate. So initially, for analyzing the circuit, the switch is been open, the switch has been closed at time t is equal to 0, but initially the switch has been open. So yes, the circuit initially, the question of 6a. So yes, your circuit will be looking before initially the switch has been closed. That is, we have only your 18 ampere current source. Why? Because your switch has been open circuited. So obviously there will be no current flowing through this wire, as a result of which is open circuited in our case. So 2 millihenry, and this is the capacitance value of the 50 ohm resistance plus minus 1 by 288 millifarads. Yes, and now we can see here that since the inductor for a very long time acts as short circuit, we have to replace your inductor by short circuit, and current remains as it is, 18 ampere current source remains as it is, and now the 10 ohm remains as it is. But we know that, and we also know that, what we know that is that capacitance is open circuited for a very long time. It is open circuited OC. As a result of which there will be no current flowing through this branch. Thus the entire current flows through this loop. So the entire current will go on repeating through this loop until so yes, we can see that IL of 0 minus, that is current that is flowing through inductor, is simply 18 ampere, since this branch is neglected because of its open circuitance. And now the entire current, 18 ampere current source, goes on repeating through this loop, as a result of which the current that is flowing through inductor, which is short circuited in this case, is 18 ampere. And since we know that inductor current does not change simultaneously, so IL of 0 plus is also 18 ampere. So also we calculate the value of VC of 0 minus. So what is VC of 0 minus is VC of 0 minus, that is capacitance voltage before initially at initial stage at t is equal to 0 minus. So this is the circuit condition at t is equal to 0 minus. And yes, in order to calculate the VC of 0 minus, here you can see the polarity is plus minus, and also we have given the polarity of capacitance as plus and minus. So we can see here that in order to calculate the capacitance voltage, it is in the, all these branches are in the form of parallel. We can see the 10 ohm resistance branch is parallel with the 18 ampere current source, as well as if you just transpose this your circuit, it will be seen as that your 1 by 288 capacitance is also parallel with this branch. So all these are in parallel connection. Since all these are in parallel connection, the voltage across your 10 ohm resistance is the same voltage across your capacitance, since all these are in parallel condition, parallel cases, which will be, let me show it clearly. So all these are in parallel, right, in this fashion. 10 ohm, so 18 ampere current source, and your capacitance this is 50 ohm. So whatever be the value of this voltage across this 10 ohm resistance is the same voltage that appears across this capacitance. So yes, in order to calculate, so the current through this is 18 ampere, which is flowing from plus to minus. The polarity is plus to minus. Since from plus to minus, the voltage across this across 10 ohm resistance is 18 multiplied by 10, which will be minus 180 volts because of its plus minus polarity. So plus minus polarity. So hence VC of 0 minus is minus 180 volts. So now second condition, at t is equal to 0 plus, what happens if the switch is closed? When switch is closed, here we can see that time t is equal to 0 plus, the circuit will appear like 2 milliampere current source, one by 288, the 50 ohm resistance branch. And now when your switch is closed at time t is equal to 0, as we can see that this switch is closed at time t is equal to 0, the same current flowing through 18 ampere, this will be 2 millihenry and this will be 10 ohm as it is. So since the switch is closed, the entire 18 ampere current goes on circuiting through this loop, whole loop. So the 18 ampere current source will not enter into either into this branch nor to this branch. It goes on repeating in through transversing this through this loop, as a result of which we can see that now since we have to calculate the value of di by dt 0 plus, I mean the second derivative of your inductor current IL, let the inductor current be IL. So yes, just we can apply your KVL through this outer loop. We can apply the KVL through this outer loop, neglecting this 18 ampere current source since it has been short circuited by this branch. Yes, we can apply the KVL to this outer loop, since we know that voltage across your inductance is L into di by dt, which is 2 millihenry multiplied by di by dt. Obviously at time t is equal to 0 plus di by dt, the voltage across inductor is given by L into di by dt, and voltage across your resistance is same, that is 10 plus 15 times IL plus voltage across your capacitance is VC of 0 plus, right? So hence we know the equation, this is the KVL by KVL. We have found this equation by using KVL. So hence the equation is 2 millihenry multiplied by di by dt at 0 plus 60 into IL of 0 plus, that is the voltage drop due to this 10 ohm and 50 ohm, plus voltage drop across this capacitance is VC of 0 plus. Since we know that this capacitor voltage does not change simultaneously, so VC of 0 plus is also minus 180 volts. I'm replacing it 2 millihenry into di by dt at 0 plus, which will be equal to, transferring these two terms on the RHS side, which should be 60 into minus 60 into IL of 0 plus. IL of 0 plus is 18 amperes multiplied by 18 amperes minus of VC of 0 plus is minus 180 minus 180. So on solving this di by dt at 0 plus, we will be getting the formula as minus 60 into 18 minus into minus plus 180 divided by 2 into 10 raised to minus 3. On simplification, we get di by dt as minus 450 kilo amperes per second. Current, the unit of I current is amperes, unit of t is seconds. We have written down the minus 450 kilo ampere per second, and now we have to calculate di by dt. Just consider this equation as equation 1. Now in order to find di by dt, that is second derivative current, that it is your second derivative current, we have to just differentiate this equation 1. Differentiate again equation 1. On differentiating your equation 1, you get 2 millihenry, which is constant, multiplied by d square I by dt square at 0 plus, which is our required term, plus 60 is constant, which will be differentiating I with respect to time t is dIL by dt at time t is equal to 0 plus, see capacitance voltage. Capacitance voltage is 1 over c integration I dt. We know that the voltage across capacitors is given by the equation 1 over c integration of I dt. On differentiating with respect to time t, this integration will be eliminated. So I by c at 0 plus is equal to 0. So yes, the equation is satisfied. And now just go on substituting the values into d square I by dt square at 0 plus 60 into the value of di by dt is simply minus 450 plus what is the value of I of 0 plus. I of 0 plus, you get it as see the value of capacitance is given as 1 over 288. So 1 over 288, which is millifarad, into 10 raised to minus 3. But we have IL of 0 plus 18, which is equal to 0. So yes, 2 millihenry into d square I by dt square at 0 plus 16 to minus 450 kiloampere. Since we can see that we have into 10 raised to 3, which is in kiloampere, so which will be minus 60 into 450 10 raised to 3 kiloampere, which will be getting the value of equal to minus 27 into 10 raised to 6 minus 16 to 450 10 raised to 3 plus 18 when divided by 1 over 288, which will be raised to minus 1 over 288, that is 1 over 288, then this multiplied by 10 to minus 3, which will be getting as 3.47222 into 10 raised to minus 6 equal to 0. On transferring this equation to the RHS part, we get d square I by dt square at time t is equal to 0 plus as 27 into 10 raised to 6 minus 18 when divided by 3.4732 into 10 raised to minus 6 whole divided by 2 into 10 raised to minus 3. So the answer of d square I by dt square at time t is equal to 0 plus would be minus 10.9 into 10 raised to 6 ampere per second square is your answer. Which is minus 10.9 into 10 raised to positive 6 ampere per second square. I hope you can see this, which is di square by dt square. So my final answer is minus 10.9 into 10 raised to 6 ampere per second square, which is obtained by solving this whole equation, that is 27 into 10 raised to 6 minus 18 divided by 3.47222 into 10 raised to minus 6 whole divided by your 2 millihenry, which is 2 into 10 raised to minus 3. On obtaining, get the answer as minus 10.9 into 10 raised to positive 6 ampere per second square. So another question of 6b, which is, for the circuit shown in figure 6b, when the switch is at position 1, steady state conditions are reached. At time t is equal to 0, the switch is thrown to position 2. Obtain the expression for current for both the cases. So the question states that initially the switch is at position 1, which is connected to position 1, so that this plus 5 volt is not considered. And at the second case, where the switch is thrown to position 2 at time t is equal to 0, and now the plus 10 volts is disconnected from the whole circuit. So the problem can be analyzed in two cases, where in first case, initially the problem which is given, where your initially the first position is connected, and this second position is obviously disconnected. So yes, we have to calculate the current in both the cases. That is, first case when the switch is at position 1, another case when the switch is moved to position 2 at time t is equal to 0. So before going to solve the problem, first we should note that at instant of time capacitance act as switching, capacitance act as short circuit, and for long time of switching, capacitor act as open circuit. So since it is switched for a very long time, that is at t is equal to 0 minus, this is the case where at t is equal to 0 minus, where the network has been drawn, the capacitor act as voltage, that is short circuit. It act as open circuit for a very long time. Since the switch is closed for a very long time, it act as open circuit. Basically at t is equal to 0 minus, that was open circuit. Since it act as open circuit, there will be no current flowing, 0. Since there will be no current flowing, the voltage drop across your 50 ohm resistance, which is V across 50 ohm resistance, is equal to I into R. Since current is 0, there will be no voltage drop. Thereby, the voltage across your 0.1 microfarad will be voltage drop across 0.1 microfarad at a time t is equal to 0 minus will be equal to simply 10 volts. Since there is no voltage drop across your 50 ohm resistance, the same voltage drop across here at this terminal. So the voltage drop at 0 minus is 10 volts. As we know that at capacitor, in capacitors, we know that V of 0 minus is equal to V of 0 plus. That is, instant before closing the switch is same as that of instant after closing the switch. So yes, the first case is considered where the current is 0. So since in the question they have asked to calculate the value of for the figure circuit shown switch position steady state at time t is equal to 0. So the next question, which is 6b, for the circuit shown in the figure 6b, when the switch is at position 1, steady state condition is already reached. At t is equal to 0, the switch is thrown to position 2. So the question is here, which states that initially the switch is at the position 1. So this branch is obviously neglected when the switch is at position 1, and at time t is equal to 0, the switch is switched to position 2, thereby this branch is neglected. So initially the question is stating that, question 6b, initially at position 1, the switch is connected to your 10 volt voltage source. So yes, and since it is not connected to position 2, obviously this plus 5 volt source is obviously neglected, because since it is not connected to this branch. So yes, and the question statement further goes like, obtain the expressions for current for both the cases. That is, there are two cases, which is when the switch is at position 1, case 1, position 1, which is this case, and second case is your position 2. Obviously you have to obtain the expression for current. So you have to find the values for current in both the cases and find the value of current at 0.01 and 0.03 seconds after switch is thrown to position 2. So before moving to it, since in this problem the switch is been at a position 1 for a very long time, as a result of which for a very long time capacitor act as open circuit, as a result of which you have to open circuit your capacitance. Since capacitance open circuit, the current which is flowing I will be equal to 0. Since there will be no current flowing, the voltage drop across 50 ohm resistance is I into R. Since there is no current flowing, the voltage drop is 0. So there will be no voltage drop across 50 ohm resistance. And what is the voltage across here? The same voltage appears as here, since there is no voltage drop across 50 ohm resistance. So voltage across your capacitance is equal to, at obviously 0 minus, is 10 volts. Since there is no voltage drop, the same voltage appears across this terminal. As we can see here, that is 10 volts is your answer. And now, since you have to find the value of current, I of 0 minus is 0 ampere. We have found out the 0 ampere. Now when the switch is thrown to position 2 at time t is equal to 0, the circuit appears like this. Now the second case is when be careful now that since capacitor is used to store the charges, as a result of which it now acts as a voltage source, because at the position 1 it has been charged to 10 volts. So I have to replace this capacitance by a 10 volt voltage source. It is a very important step. And now you have to find the value of current through this. In order to find the current through this, so the net voltage due to 5 volts and 10 volts would be 5 volts. The net voltage is equal to net voltage due to both the loops. And we have the formula of current through finding when the switch is at position 2, when switch is changed its state. So we have formula which goes like I at any instant of t, which will be minus v by r into e to the power minus t by rc minus t by r into c. So yes, since we want at a position 0 plus, which will be minus v by r, the net voltage due to 5 and 10 is obviously 5 volts, divided by resistance is 50 ohm, into e to the power of minus, what is your time value? Your time value is, let it be as it is, and r into c, r value is 50 multiplied by c. Your c value is capacitance values, which is given as 0.1 microfarad, 0.1 microfarad, and the time value, since they have given it for the cases, we can see here that switch is thrown to position 2. Obtain the expression for current for both the cases. Find the value of current at 0.01 at 0.01 seconds. Please note that, make sure that your time is in seconds. So yes, on calculation you get the value of 0.01 as 0 ampere, and second case is that you have to calculate the value of current at 0.03 seconds, which will be I of 0.03 is equal to minus 5 by 50 into e to the power of minus 0.03 divided by 50 into 0.1 into 10 raised to minus 6, which will be also equal to 0 ampere. And now we have solved the question, and this is the solution for this. The next part is of your unit 4, where they have stated the question as find the inverse Laplace transform of the following: x of s is equal to s plus 1 s square plus 4s by 13. Please note that this x of s indicates that this question is in frequency domain and you have to convert it into time domain, obviously by using your inverse Laplace method. So a simple mathematical question, which is x of s is equal to s plus 1 divided by s square plus 4s plus 13. First I modify the denominator as follows, as s plus 2 whole square will be s square plus 4 plus s square plus 4 plus 4s, right? So I will be remaining with 4 plus, I should add now 3 square, which will be 9, 9, 10, 11, 12, 13, yes, I should add 3 square, which will be the same as that of your previous denominator, and then I split the particular denominator as, let me just write the numerator as s plus 2 minus 1 divided by s plus 2 का whole square plus 3 square. Now splitting the denominator into each of the numerator terms, which will be s plus 2 divided by s plus 2 whole square plus 3 square and minus 1 divided by s plus 2 whole square plus 3 square. And we can see that it is in the form of cos, as you know that cos of st is equal to s square divided by s square plus e square, which is the same form as that of this. Since s plus 2 is added, we will be getting cos s plus 2 multiplied by t. Whatever be the constant, we just ignore it. And here we can see that a 3 is missing, so we multiply and divide this by 3, which will be getting 3 1 by 3 multiply by 3 divided by s plus 2 whole square plus 3 square, which can be seen that it is in the form of cos s plus 2 into t, which is in the form of sine term. Writing 1 by 3 as constant, this will be in the form of sine term. Since s plus 2 is there, we should take it out as e to the power of minus 2t into sine of constant is 3t. And this is how the problem is solved. And so we get the final answer as cos of s plus 2 into t minus 1 over 3 e power minus 2t into sine of 3t is your transform domain from your frequency to your time domain, that is from frequency to time domain. So the next sum, which is 7b, use the Laplace transform to evaluate v0 of t for t greater than 0 for the circuit shown in figure 7b, assuming v0 of 0 as 5 volts. Yes, they have given v0 of 0 minus as 5 volts, that is the voltage across this before any time is 5 volts. So yes, So this is a it is a Laplace transformation numerical. So in solving any of these inverse Laplace transformation numericals, first three steps to be noted. That is, first convert to frequency domain, then you have to evaluate, and third step is convert back to time domain. So these are the three steps in solving any of this inverse Laplace transformation numerical. So yes, we convert this time domain first to frequency domain, first to your frequency domain, yes, and we convert this into frequency domain as 10 ohm, 10 ohm, yes. First conversion of this of voltage source into frequency, right? 10 is constant, we will write 10 as it is, and e power of minus t, the Laplace transform or the inverse Laplace transform of this e power of minus t is 1 divided by s plus 1, 1 divided by s plus 1 plus minus, and Laplace transform of this unit function is obviously equal to Laplace transform of this unit is obviously equal to 1, which will be not considered, and 10 ohm, 10 ohm, the same distance remains the same, which is 10 ohm and 10 ohm. The next part is your where transformation of your capacitance. Please note that while transforming of your capacitance, since we know that capacitance is used to store charges, right? And these stored charges can be represented either into voltage form, in the form of voltage as plus minus V naught of minus divided by S, which is capacitance. Equivalent capacitance is represented as 1 over Cs. Please note it down. This is the first case of representation of charges, or either it can be represented in form of current as C into V of 0 minus 1 over Cs. This is the second case. So you can represent your capacitance either in the form of voltage or in the form of current. So since there is a parallel branch, since the question is of parallel branch contains more number of parallel branches, I replace it with a current source. So capacitance, equivalent capacitance in frequency domain is given by 1 over Cs, which will be C, and I will be representing this in the form of parallel current. So it will be C into V of 0 minus S. And now 2 into delta of t, which will be current to source 2 as it is, because Laplace transform of this unit impulse function is 1. Unit impulse function, this is a representation of unit impulse function as delta of t, which will be equal to 1 ampere. Yes, so we have successfully converted our time domain circuit into a frequency domain circuit containing of S parameters, right? So yes, solving the question, since you have to calculate the voltage across this capacitance, I represent this V naught of S. This is the voltage at S domain. Please note that S is represented as for frequency domain, and we apply the KCL. By applying KCL, we apply KCL, that is Kirchhoff current law. So yes, you can see here, before going on to by applying KCL, we reduce the network furthermore, which will be plus minus 10 divided by S plus 1. This will be 10 ohm. This will be 10 ohm. And here we can see that we have your capacitance value as 0.1 farads. So 1 divided by 0.1 will be 10. S will be as it is. And this will be, what is C value? C value is 0.1. And what is V of 0 minus, which is already given in the question, which is 5 volts. 5 into 0.1 will be 0.5 amperes. This will be V naught of S. And this will be V naught of S. The 2 ampere current source remains as it is. So yes, we have to find out the voltage across this branch, across this capacitance. Yes, by apply KCL. Now we apply KCL. V naught of S, this is a mean voltage source, minus this, which will be 10 divided by S plus 1 minus V naught of S divided by resistance R, which is 10 ohm in this case. It is in the form of, since we apply KCL, which gives the parameter of current. Current is nothing but voltage by resistance. We can see this is a voltage parameter, this is a voltage parameter, this is a voltage parameter, which is subtracted and divided by resistance parameter, which will give me, this is 10, which will give me a current parameter, which is V divided by R. And since this is the leaving current, this is also incoming current. This is, see, just make sure that this is leaving current, and this, due to this voltage source, is incoming current, and this is also incoming current. By KCL we write incoming current. KCL means that incoming current is equal to outgoing current, right? See, these parameters, that is 10 divided by S plus 1 and V naught of S is the incoming current, as does this plus 0.5 plus 2 ampere is equal to, these all are incoming currents, with outgoing currents, which is V naught of S divided by 10, that is voltage by resistance, which is current, and here plus V naught of S divided by 10 over S. I hope this step is clear, where we have separated the incoming currents as well as the outgoing currents. Since we can see here, due to this voltage source, the current will be flown downwards, and due to this voltage source, obviously the current will be flown downwards. Obviously these parameters are written in the right hand side, whereas your, due to this 10 plus S, 10 divided by S plus 1 and this voltage source, the incoming current, as since the 10 divided by S plus 1 is a greater voltage, this will be pushing the current towards your V naught of S. This will be incoming current, and this 0.5 is obviously incoming current, which will be ending towards this point, and 2 ampere current source is also an incoming current, which will be ending towards this point. And we have separated the incoming current as well as the outgoing current by simple KCL method. Yes, now we just evaluate the following equations. As I separate this denominator as 1 divided by S plus 1 minus V naught of S divided by 10 plus 2.5, which will be equal to V naught of S by 10 plus S into V naught of S by 10. And then I separate this V naught of S into right hand side, which will be 1 divided by S plus 1 plus 2.5, which is equal to V naught of S plus V naught of S will be 2 times of V naught of S divided by 10 plus S into V naught of S by 10. I take out this common, 1 by S plus 1 plus 2.5, which will be equal to 2. I take V naught of S by 10 as common, which will be S plus 2. I will be remaining with the term S plus 2, and I just cross multiply the 10, which will be 10 divided by S plus 1 plus 25, which will be equal to S plus 2. And yes, now I take the LCM across this LHS, which will be 10 plus 25S plus 25 divided by S plus 1, that is equal to V naught of S into S plus 2. Now an evaluation of this will be 25S plus 35 divided by S plus 1 into S plus 2, which will be equal to V naught of S. So the equation which is appearing here is this, which is 25S plus 35 divided by S plus 1 into S plus 2, which is equal to V naught of S. I simply take this by partial fraction method, which will be 25S plus 35 divided by S plus 1 into S plus 2. I can represent the partial fraction as A divided by S plus 1 plus B divided by S plus 2. On taking LCM, you get 25S plus 35, which will be equal to A into S plus 2 plus B into S plus 1. On evaluation of this by trial and error method, I put S is equal to minus 1. I put S is equal to minus 1. This term will be ended up with 0. So minus 25 plus 35 will be 10, which is equal to A into 1. So A value is 10. For my B value, I put S is equal to minus 2. I terminate this term. It should be minus 50 plus 35, end up with minus 15, which is equal to B into minus 1. Minus it cancels. I will be remaining with the value of B is equal to 15. So I'm replacing this term as V naught of S, which is equal to 10 divided by S plus 1 plus 15 divided by S plus 2. Now I evaluated the second step, which is of evaluation. I have done the evaluation, and now I convert back into time domain. Since the question asked here is to calculate the voltage V0 of t at a time t is equal to 0. Here we can see that it is in the time domain. Since this is in the frequency domain, I have to convert in step 3, which is back to time domain, which will be V0 of t. Just apply your inverse transform method. 10 is constant. What is inverse of e s plus 1 is e power minus t. Similarly, plus 15 into e power minus 2t. Inverse Laplace of s plus 2 is e power minus 2t u of t. So this is your final answer. Or basically this is a quite lengthy problem, but you can solve it if you know the basics of it. The next problem, which is 8a, for the circuit shown figure in 8a, obtain Vc of 8 for time t is equal to 0 using Laplace transform. Here in this question, they have not given the value of Vc of 0 minus. So we need to calculate the initial value of voltage. So yes, in figure 8a, they have given the circuit problem where the switch is being closed for a very long time, and at time t is equal to 0, switch is being open to 6 ampere. So the switch is being closed for a very long time, 3 ohm. For a very long time, your capacitance acts as open circuit. Yes, you have to open circuit it. There will be no current flowing through this branch, so you can just neglect this branch. And we have to calculate the Vc of 0 minus. In order to calculate the Vc of 0 minus, you should know the value of current flowing through it. If you know the value of current that is flowing through 3 ampere, you can just calculate the voltage, and this voltage will be same across this capacitance voltage. Yes. Now in order to calculate the value current flowing through a 3 ampere current source, you have to apply your current division rule, which is current flowing through a 3 ampere is mean current is 2 ampere multiplied by resistance of other branch is 6 divided by 6 plus 3, which will be equal to 12 divided by 9, which will be answer 9 ones are yes 1.333, which will be 1.3333 amperes. And in order to calculate the voltage across your 3 ohm resistance, which will be current into resistance, current is 1.333 multiplied by 3, which will be equal to 4 volts. So yes, and V of 0 minus is 4 volts, and the capacitance voltage is 4 volts. Now we have calculated the 4 volts. Now by applying the previous steps, which is first step, you have to convert this into frequency domain. Converting this into frequency domain, you get it as 2 ampere current source in converted into frequency, and we'll get it as 2 bias. And please note that for frequency domain, here we can see that at time t is equal to the switch has been opened, so this branch is open circuited. No need to consider this branch. 3 ohm remains as it is, and so 0.5 farads is your capacitance, which is replaced by 1 over C into S. I replace this with the current source, is C into V of 0 minus. We know the value of 0 minus, we can calculate it. Yes. For simplifying the network, we get 2 by S, and 3 ohm resistance remains as it is. As capacitance, you can see that the value of capacitance is C is 0.5. 1 divided by 0.5 is obviously 2 divided by S, and 1 divided by 0.5 is 2 divided by S remains as it is, and C value is 0.5. 0.5 when multiplied by 4, you get 2 ampere current. I represent it as V of S. I calculate the value of V of S. So V of S, so I apply the basic KCL equations. In order to solve it, apply KCL equations, that is current entering, I entering is equal to I leaving. Thereby, as a result of which, here we can see, as a result of which the current entering is equal to current leaving. Both the current sources are entering the point V of S. So I write it down in the left hand equations by 2 by S plus 2 ampere. These are the current that are entering to this point. Similarly, current leaving is this current, that is V of S by 3 plus V of S divided by 2 by S, that is voltage divided by resistance, which will give me a value of current. So yes, just simplifying the equations, 2 plus 2S divided by S, which will be equal to V of S 1 by 3 plus S by 2. On solving, 2 plus 2S divided by S, which will be equal to V of S into 2 plus 3S divided by 6. Just cross multiplying these equations, we will get 12 plus 12S, which will be equal to V of S into 2S plus 3a square, and you get v of s equal to 12 plus 12s divided by 2s plus 3 square. Further solving these equations mathematically, you get it as 6 over s minus 2 divided by s plus 2 by 3. And since we have evaluated the step, we can just, by step 3 we know that we have to calculate back into time domain, back to time domain. So back to time domain is by applying inverse Laplace, you get v of t, which is inverse Laplace of 1 by c is simply 1. So 6 into 1 minus 2 remains as it is, which will be 2 remains. If we take 2 as your constant value, you get 2 into e power of minus 2 by 3. Since it is a form of e power minus 2 by 3, what is the Laplace transformation of e power 2 by 3? Which is s plus 2 by 3. So inverse Laplace of s plus 2 by 3 is simply e power of minus 2 by 3 into t, which is u of t volts. So if calculated the values, so thereby your voltage at time t is greater than 0 is equal to 6 minus 2 into e power of minus 2 by 3 t. U of t is basically unit step function times volts. The next question, which is of 8b, evaluate the Fourier constants for the waveform shown in the figure 8b. So here is the Fourier signal waveform, which is this is the Fourier signal function f of t with respect to omega t, and so minus 6 and minus pi by 4, the value of 0, this is plus 4 pi, 7 pi by 4, 2 pi, 3 pi. So this is how this is the Fourier signal, which is in the y-axis, which is represented by f of t, and in the x-axis, which is omega t. So first we have to define how the function is defined in what intervals. So the function f of t is defined in the intervals as shown. That is, as you can see here, from the function value at time t, which is less than pi, less than 0, is equal to 4. Yes, 4, and is equal to from time period between 7 pi by 4 to pi, which is equal to 0, 0 at intervals less than 7 pi by 4 and less than pi, and at the intervals 2 pi to 7 pi by 4, it is equal to minus 6. Yes, minus 6 at your intervals t less than 2 pi and less than 7 pi by 4. This is how the function f of t is basically defined. The function f of t is basically defined in these intervals. That is, we have plus 4 for the intervals t less than pi greater than, that is t less than pi greater than 0, and 0 for the intervals t less than 7 pi by 4 and greater than pi. Yes, and minus 6 for the intervals less than 2 pi greater than 7 pi by 4 as minus 6. So just you have to apply your basics of Fourier transform. So a naught, which is equal to, and you have to calculate the, by means of Fourier transform, that you have to calculate the values of a naught, an, and the value of bn. You can just apply your simple formulas as a naught by 2 pi from splitting those intervals from 0 to pi, which is 4 into omega t dt. Just make sure that you differentiate with respect to your omega t, plus this is obviously the whole entire interval will come to a value equal to 0, and plus that is your greater interval 2 pi with 7 pi by 4 minus 6 into omega t d omega t. That is, we have to differentiate with respect to that of omega t. Since the x-axis is given with respect to that of omega t, so I have to differentiate with respect to that of omega t, which will be 4 into differentiating with respect to omega t will give me a value of t whole square and minus 6 divided by 2 omega t whole square. This is from the interval 0 to pi, and this is from the interval 7 pi by 4 to 2 pi, and substituting this equation, we get 2 of pi square minus 0 minus 3 of 2 pi whole square minus 7 pi by 4 whole square. On solving this, you get answer equal to minus 1.27. So this is your E naught value, and now we have to calculate the value of En. So the value of En is calculated as this question paper just troubles me, and E naught is 2 by T naught. What is T naught? T naught is basically your entire time period from 0 to 2 pi. 0 to 2 pi, or you can just simply write it down the direct formula as 0 to 2 pi f of t into cos n omega naught t times d omega t, since you are differentiating respect to that of omega t. Here we can see that 2 by t naught is your entire time period from 0 to 2 pi, and the intervals from 0 to 2 pi. Yes, you can just substitute 2 by 2 pi will give me a value 1 by pi, and just splitting the intervals, that is we have from 0 to pi as from 0 to pi we have 4. F of t is 4. F of t values are 4, 0 and minus 6. F of t is 4 for the interval 0 to pi into cos n omega naught t, plus similarly 0 not at all considered, and 7 pi by 4 to 2 pi, which is minus 6 multiplied by cos n omega naught t times d omega t. Just make sure you write it as d omega t, and this also differentiating the respect to that of d omega t. Now we have to go on differentiating it, which will be 4 is constant, and the differentiation of integration of cos n omega naught t is simply sin n omega naught t, since you are differentiating with respect to omega t, whereas our n becomes constant from 0 to pi. Minus 6 is constant, divided by take it out and already constant. What is cos n omega naught t is obviously again sin n omega naught t, where n is constant. I have taken it out, and 7 pi by 4 to 2 pi. Now yes, and substituting those values, that is 4 by n, and sin n pi is obviously 0, and sin 0 is obviously 0, so the whole term is 0 minus 6 by n. So sin 2n pi, which will give sin 2n pi, which will give a value of 0, because n pi, any integer of n pi is obviously 0 of sin, and plus 7 by 4 will give a value of root 2 by 2. Yes, which will end up me a value of equal to 6 divided by c, that is simply I can write it as 1 over pi. This will be 0 minus 6 by n, 0 minus sin of n 7 pi by 4, which is obviously sin n 7 pi by 4. See, 7 sin pi by 4 is defined as root 2 by 2, but 7 n 7 pi by 4 is not defined. So yes, which will be taking out minus into minus, is plus 6 divided by n pi is obviously constant value into sin n 7 pi by 4 is the value of En. The value of En not, the value of En is calculated. To calculate the value of Bn to be calculated, so yes, the Bn formula is very simple, which will be 1 over 2 by T naught. 0 to 2 pi is your interval into f of t into, but the only change with respect to Bn is sin n omega naught t times d omega t. Make sure you write d omega t, not dt. And then 2 by t naught is entire time period, which is 2 pi, which is equal to, let me write it down, t is equal to 2 pi, so you get 1 by pi. Splitting down the intervals from 0 to pi as 4, 0 to pi as 4 into sin n omega naught t d omega t plus, and 7 pi by 4 to 2 pi as minus 6 sin n omega naught t times d omega t. And solving, we get it as 1 over pi. 4 is constant. What is sin n omega naught t? Integration is 4 by n minus 4 by n cos n omega naught t due to pi, because sin nt differentiation is minus cos nt. So yes, we get this where n is constant, taking it out, minus 6 by n, and integration of sin is minus cos of n omega naught t, integration from 7 by 4 to 2 pi. Obviously n is constant, I've taken it out, and simplification 1 by pi minus 4 by n cos n pi is minus 1 to the power of n, minus cos 0 is 1, minus into minus plus 6 by n, cos 2n pi minus cos of n 7 pi by 4, which will be equal to 1 over pi minus 4 by n, and this will be minus 1 to the power of n minus 1 plus 6 by n, and here we have cos 2n pi, which is obviously gives a value of 1, and cos n 7 pi by 4, let it write 7 pi by 4 as it is, and this we get the values as bn equal to 1 by pi minus 4 by n is constant, and minus 1 to the power of n minus 1 plus 6 over n, 1 minus cos of n 7 pi by 4 is your value of bn. So we have come to the next part, which is your unit 5, where I will be solving only the numericals based on magnetic circuits, which is of 9a and 10b. So the question is of 9a. So the circuit shown in figure 9a, find the flux produced in the, you have to calculate the flux that is produced in the first coil, in the first winding, and voltage that is induced in the second coil. So the figure is quite simple, which is here. So they have given to find out the value of the flux that is produced in your first coil as well as the voltage induced across your second coil. So this is the circuit diagram, which is shown here. Coil L2, coil L1 with the voltage induced to be L2, and the voltage induced here is nothing but VL1, whereas K is the coefficient of coupling between the two coils. Due to the current that is flowing through this coil, there will be some magnetic field, and due to current flowing through this coil, there will be some magnetic field due to both the magnetic field which will be linking to either both of the coils, thereby which is represented by K, which is coefficient of coupling. The value is given by 0.75, and the number of turns in secondary is given by 500. The number of turns in secondary is 500. Similarly, L1 is equal to 10 millihenry and L2 is equal to 20 millihenry. So before moving on to solving the parameters what to be calculated, let us calculate the value of mutual inductance, which is given by the formula K into root L1 L2. So value of K is 0.75, and the root of L1 L2 is 10 into 10 raised to minus 3 multiplied by 20 into 10 raised to minus 3, which will be 0.75 multiplied by square root of will give me a value equal to 0.01060 is your value of mutual inductance in terms of Henry. So the value of M is calculated here, which is in Henry, and now we have to calculate the value of the voltage induced in the secondary coil. So the voltage induced in the secondary coil is basically given by the formula is equal to M into di1 by dt. Also we have another formula which is given by 512, that is N2 into d512 by dt, where your 512 is the flux that is linked in one due to 2. So N2 is number of turns in secondary. Since we can use either of the values, but since they have not given the value of the current, and as well as we don't know the value of the flux induced in the secondary coil, which is 0.01060 multiplied by di1 by dt. So let us keep this equation as it is, and let us find out the value of the flux induced in the primary coil, which is 511. So we know the relation of coefficient of coupling as K is equal to 512 by 511. So if I know the value of 512, I can just calculate the value of the coefficient of coupling K. Yes, I should know the value of 512. In order to obtain the value of 512, we know that mutual inductance M is equal to N2 into 512 by I1. Since I want to know the value of 511, I need to know the value of 512. but the question asked here is to find out the value of I11, which will be m is equal to n2 into k into 511. Directly I can use this formula in this equations in order to calculate the value of I11. Since I need to calculate the value of I11, yes, and since I don't know the value of I1, let it keep it as it is. So the value of m is which we have calculated as 0.0. But just transfer the equation, which will be m, modifying this above equation, which will be m is equal to m multiplied by I1 divided by n2 multiplied by k, which will be equal to 511. So value of m is 0.01060 multiplied by the value of I1 is not known, divided by n2 is 500, and multiplied by coefficient of coupling k is given by 0.75 is your value of I1. So in either of the cases, if the value of the current is given in this question, you can just substitute this current in this differential form and calculate the value of the voltage that is induced across it, and by using the value of current which is given in the question, and you can also calculate the value of flux induced in the primary coil. Since they have not given the value of current I1, we can keep these equations as it is, and this is how the problem is solved. The next question, which is 10b, obtain the expression that is for the circuit shown in the figure 10b, obtain the equivalent impedances. You have to calculate the equivalent impedances due to all these three coils, which is the question 10b. Which is 10 Henry, 8 Henry, 6 Henry. Oh, sorry. The dot terminal is at this position. 0.2 Henry. And the linking inductance between this coil 2 and coil 3 is 0.3 Henry. Similarly, the dot terminal is placed at the last of this terminal, and the linking inductance between this coil 1 and coil 3 is 0.4 Henry. So I have to calculate the equivalent impedances due to all these three inductance coils. It should be L equivalent. Now due to one, L equivalent will be due to coil 1 plus due to coil 2 plus due to coil 3. So due to all these coils, there will be resultant L equivalent. So first coil 1, due to coil 1, so main coil is 10 Henry plus the linking inductance between coil 1 and coil 2. Since we can see that here the dot terminal is placed at the first, that is the current entering into the dot terminal, whereas in coil 2 the current is leaving the dot terminal. The placement of the dot terminal is very, very important in solving such type of numericals. So hence minus 0.2 Henry, and whereas in coil 1 and coil 3 current is entering dot terminal, whereas in coil 3 it is leaving the dot terminal, so hence minus 0.4 Henry. On solving, 10 minus 0.2 minus 0.4, which will be minus 0.2 minus 0.4 will be minus 0.6, which will be 9.4 Henry. Similarly, due to coil 2 is 8 Henry and plus, so the linking between 1 and 2, coils 1 and 2 is current is entering, current is leaving, so hence minus 0.2 Henry. And in this case, the current is leaving the coil 2 and current is also leaving the coil 3, hence adding both the inductance value, which is 0.3 Henry, the mutual inductance value 0.3 Henry, which will be 8 minus 0.2 plus 0.3, which will give me 8 plus 0.1, which will be 8.1 Henry. Similarly, L3 would be coil 6 Henry, inductance value of this coil, that is 6 Henry. And now the mutual inductances, that is in coil 1 and 3, here we can see that current is entering the dot terminal, and here the current is leaving the dot terminal, which is minus 0.4, the linking mutual inductance between coil 1 and coil 3. Similarly, the linking mutual inductance between coil 1, coil 2 and coil 3 is leaving the current leaving the dot terminal, current also leaving the dot terminal, which will be plus 0.3, which will give me answer equal to 6 Henry minus 0.1 Henry, which will give me a value of 5.9 Henry. Now adding, in order to get equivalent impedances due to all these three coils, will be L1 plus L2 plus L3, which will be 9.4 Henry plus 8.1 Henry plus 5.9, which will be equal to 9.4 plus 8.1 plus 5.9, which which will give me a value equal to 23.4 Henry. So this is how the problem is solved. And this is how the problem is solved. By adding all these inductance value, that is L1 plus L2 plus L3, you get the net equivalent impedance due to all these three coils as 23.4 Henry.